All right. I'm going to work through the first example in this section 4.4 is optimization 1. This section is about finding, absolute extrema using the derivatives. Okay, so when you try to find the absolute extrema of a function, you're going to do it in 2 steps. The first steps is to, locate the critical numbers, and then the second step is to compare the values of the function at the critical numbers and the function value at the endpoints. Okay, because the relative extrema are determined or included at the critical numbers. So if you include all the critical numbers and endpoints, that will tell you where is the absolute extrema or where they are. Okay. So in this example, we need to find the absolute extrema of the function f equal to x squared on the interval from -1 to 2, the closed interval. Okay, from -1 to 2. So let's just work out the problem. This is a pretty simple function. We can illustrate the steps of locating absolute extrema in this simple example. So first, let's try to find critical numbers of the function f. Okay. So what do we do? You just take the derivative of this function. It's very, very simple. I guess everyone knows what the derivative of the function is. Okay, you just take the derivative of x squared, you're gonna get 2 times x. Okay, so you put 2 in the front, the exponent, and lower the exponent by 1. So 2 minus 1 is 1, so 2 times x to the 1, but x to the 1 is just x, so that's 2x. And then the next thing is to actually set the first derivative equal to 0 and solve it. Okay. So then we're gonna get the critical numbers. So in this case, it's extremely simple, as there's only one critical number. So that means we got 2x equal to 0. And obviously, the solution for the equation is just x equal to 0. Okay. So we got x equal to 0. So there's only one critical number. And then, this will be either a, relative minimum or relative maximum, but we don't have to worry about that. We don't have to find where there is a relative maximum or relative minimum. Instead, we only need to compute the function value at this point, and then compare the function value at the endpoints -1 to 2. Okay. So the second step is to compare the function at the critical number and so remember we consider this function f on the closed interval from and 2. So all right. So what we do is just plug in 0, -1, 2 into the function and see, which one is the largest, which one is the lowest. Okay. So let's just do that. So we'll get f of x equal to x squared. So we can easily find out f of 0 equals x squared. So that's 0 squared. Obviously, we got 0 in here. So, and then we plug in -1 for x. Therefore, -1 is just the -1 squared. -1 squared is +1. Okay, it's +1. So that's the second point. And then we got another endpoint, x equals to 2, so plug in 2 for x. So we get 2 squared, and that gives a +4. So now compare the values of the function at those points. We find the lowest point is actually at x equals 0. So that's the function f has the absolute minimum at x equals 0. Okay. And the absolute maximum at x equal to 2. So 4 is the highest. So that's the answer, So this is the lowest point of the piece of the curve. Okay. And this is the highest point for the piece of the curve. It's not the radial maximum minimum, it's the absolute maximum minimum because they are the lowest or highest points of the curve on the whole interval. And the lowest value of the function is actually 0, and the highest point or the maximum value of the absolute maximum is 4. Okay, and x equal to 2, I'm sorry. The maximum value of the function in this closed interval is 4, and it occurs at x equal to 2, and the absolute minimum of the function is 0, and it occurs at x equal to 0. All right. So pretty straight.